Just a small correction to that introduction. At the core, I'm a numerical analyst. I think Manchester is sort of one of the really big numerical analysis departments in the UK. But a lot of the majority of the work I do is related to molecular simulation. And so what I want to do in this talk is just show you how I use Julia, how I use Julia as a numerical analyst, and why I'm finding it more and more productive the longer I use it to keep extending, keep the. Anyways, you will see this. And so one comment is this is actually the first talk ever I'm giving on code rather than theorems. And so if the whole thing's chaotic and so on, it's something you'd actually like to understand, but I glossed over it, just stop me. I probably have too much material anyways. I'm just going to then skip some things. It's no problem at all. Right. So this is molecular simulation in one picture. Right? It's a chemistry tool set in a computer. I have no idea what that molecule is, but you pick some atom species, then you say, okay, there's a bond here, there's a bond there, and I'm going to model that bond in this way and that one in this way, and then let me add a hydrogen there, and so on and so forth. And then you've got this in your code. You press a button, and it's going to run something for you. It optimizes the geometry of the molecule. It runs Newtonian dynamics for a while, and then you extract some quantity from that. So in sort of more mathematical terms, is that actually a laser pointer, or should I just use the mouse? Okay. Let me sit down. So in more mathematical terms, it could be just like that. Right? Newtonian dynamics. If you want to keep the system you're simulating at a specific temperature, you add some noise to it and control that in a way, so that the oscillation of the atoms, which is the temperature, is under control. Or you might just want to just know the equilibrium. You minimize the energy E, there's a potential energy of the system. But you actually might want to know how you jump from a minimum to a minimum. In that case, what you want to find are the saddles between the minima. And you can keep going. I mean, there are lots and lots of problems that are very simply stated in mathematical terms, and some are easy to solve, some are incredibly hard to solve. For example, the saddle search is essentially an unsolved problem. And there is a lot of fun numerical analysis to be done. To prepare this talk, I try to keep track of what happens in Julia in molecular simulation, but to prepare this talk I did another overview, and not much has changed actually. So the very first package that I ran into ages ago now is Jumos, and a great name, a great logo, and then the guy just said, oh, I don't like Julia anymore, I started working with Rust. That's a shame, but I think he was trying to do too much too soon, all at once, and that was the real problem. I still sort of try and be in touch with him. But anyways, that's that. I found, and I think this is a relatively new code, somebody actually trying to implement a full quantum chemistry code in pure Julia. I hope that will work out. It would be great to have that available. And then a few random things I found report by some graduate students. They never published the repository, unfortunately. And then a few packages that don't do simulation as such, but more focus on the analysis. So you do the simulation in another package, then import the data into the analysis in Julia. So I'll get to the packages that I'm working on myself, but my point is that there's actually very, very little right now. Definitely people who do molecular simulation in Julia are a very small minority. Hopefully I can help to change that, but we'll see. So what I want to do now is talk a little bit about my own research, and that to show why I'm interested in working in Julia. And then I'll introduce the package that I've been working on for most of the past few months. So the standard algorithms that I mentioned, optimization of geometries, it's basically just continuous optimization. You have an objective, you minimize it. But then there's obviously the saddles and so on. Sampling, Markov chain Monte Carlo, for example, comes up a lot. I mean, molecular dynamics, in fact, you can think of just as a sampling scheme. That's all it is. And if you actually believe in the trajectories you're computing, the statistics of the trajectories are the important things in reality. And I've worked a little bit on preconditioning in molecular simulation, which is something that is barely known in that community. And I'll show some of the results of that. But the bulk of my research for the past 10 years or so have been multi-scale methods. And these are questions like you have a quantum mechanical model for some process, typically materials in my case, but it could be molecules. And how can you... So the computational cost with these quantum mechanical models is just astronomical. You cannot afford to simulate the systems you're interested in, and so you try to find ways to coarse grain. And this is the thing I want to introduce quickly. And all the ideas that I'm developing here are slowly being moved into these Julia packages, but I'll say more about that in a minute. Okay, so here is a short description of such a multi-scale scheme. This is very minimalistic. And so anybody who knows anything about quantum chemistry, I apologize for how naive this is going to look, but hopefully it sort of gives just the gist of the idea. So when you have interatomic potentials, classical potentials, they look like this line here. So you have some positions, yi, and then you write the total energy as a sum over the sites, which are the atom positions. And to each site you assign an energy, EI, a site energy, which depends on a small neighborhood, namely all the positions that are at some distance from the one you're sitting in. And if this interaction range is reasonably small, between 30 and 60 atoms typically, then you can think of that as order n costs. No problem to run simulations with that. You have usually cheap functional forms for these site energies, and so on and so forth. So here's the classical example, the first one you would write down if you want to tell somebody about a molecular simulation. You can see this looks very simple. And then there's quantum chemistry, on the other hand, which are sort of the ab initio models that supposedly approximate Schrödinger equation. And and the gist of it is this: you have a Hamiltonian, you solve the eigenvalue problem that gives you the energy levels that electrons can occupy. And then rather than, as an interatomic potential, summing over sites and assigning site energies, you're summing over energy levels and assigning an energy to each energy level. So this, what's in here is energy times occupation number plus entropy. It's not so important for this talk what exactly goes into the F. All right? And the difficulty here is that these epsilons, the eigenvalues, are nonlinear global functions of the Hamiltonian, of the atom positions which go into the Hamiltonian, and so you have these. There is no obvious separation like this one here. Okay? And so the thing that I've been thinking about is how to create such a separation, because what you can then do, if you could create a decomposition, a spatial decomposition of this energy, then you can do things like this. You can separate it. So in this case, this is a simulation of a crack propagating through a slab of silicon, and there is a sort of an interstitial, a foreign atom in this interstitial, in this silicon slab that I think it makes it more brittle. I think that's the point of the simulation. Anyways, there's, because of this extra atom, there's a lot of interesting chemistry going on at the crack tip. But this size of blue here, that's about the maximum you can afford to run a quantum chemistry molecular simulation with, but because of elastic far fields that are generated, or because of elastic waves that go away, so when the crack opens, a wave goes out, because something has to happen to that. You can't just have it bounce back from the boundary of this blue region, so you have to couple it to something on the outside, and that's where these multi-scale schemes have to come in. You somehow have to decompose your system into a quantum region and something cheap on the outside, and if you can achieve to do this, then you can run simulations like that. And this has been under development, I think, for the last 10, 15 years. People fudge something, and some things work better than others. And one of my main focus of my research right now is to put this really sort of on a firm theoretical footing. So here's now how you can achieve this decomposition. You have your total energy again, right? It's sum over occupation numbers, and then what I do is I add in 1. So this sum over I, these CS, those are eigenfunctions, they're normalized. So this sum here is just 1. And then you interchange summation between energy levels and atom positions, and suddenly what you've got is something that looks like a decomposition. And you can, and it's surprising, because, at least to me it was initially, it isn't anymore now, but despite the fact that those energy levels and the orbitals, the eigenfunctions are all global objects, they depend on everything, spatially, it turns out that decomposition is actually local, in the sense that if you have an atom here, you compute the associated, so this red thing would be the associated site energy for this atom. You change something far away from it, and then that site energy changes in an exponentially small way. That's what this theorem here says. And so now, what I want to understand how this constant here matters. For example, the constant in front here matters, and I can prove qualitative theorems that give you that. But I really want to understand what happens quantitatively. I want to test this idea on actual problems. Okay, but so just to show you then how once you have this, how you use this, well, then you now have a decomposition of energy. You can now do the following. You can split your region, here's a cartoon, into a quantum region and a classical region. In the quantum region, you keep your exact site energies. In the quantum region, you approximate them by something else. For example, it could be as simple as a Taylor polynomial. And once you have that, you get proper rigorous theorems with error estimates and everything. So, for example, if you can see a speed up of a pure quantum simulation in terms of quantum region size. So here the R is the radius of the quantum region which you're simulating against one of those multi-scale simulations. Theta's are really not so important, but you basically the better the approximation qualities of your site energies are, the faster rate of convergence you get. So you can really get huge speed ups, which you can also see numerically. So in this graph at the bottom, what you see here, the black line is the convergence rate for a pure quantum simulation, and the red and blue lines, which are right on top of each other, are convergence rates for two types of these multi-scale schemes. And say if your target is 1% accuracy in geometry, right, you get this with a very moderate quantum region size. If you wanted this with a pure quantum simulation, you need to go to huge systems that you cannot afford anymore. So in the implementing this little graph, this thing here, that was actually the first Julia code I wrote. And I didn't do this for a real quantum chemistry model. That was way too ambitious. So I implemented sort of a toy Hamiltonian. I just made something up that looked vaguely right, and then the hard part was to implement these site energies. Okay, so here's the formula again. Actually, the site energies were not the hard part. I'll explain more. This is the part I want to show in more detail. And then there's a bit of boilerplate code you have to put around that in order to, at the end, get to these graphs. But that part's the interesting part, and the one that I'm still working on now. So how does this look like? And this is not the way I wrote it the first time. This is how I would write it today, if I do this. Okay, so here's the site energy again. So what do I need? I need to get my positions from somewhere. Doesn't matter where they come from. And then I need to implement a Hamiltonian. And it can be done in this case. I said it's a pure toy model. I make up some function. It's not the function is not completely random, but I have an idea where it comes from. But I make up some function that tells me what the entries of the Hamiltonian are. So I have a big matrix, and what are the entries? And then I can just do this in a single line where you write the comprehension. You can do a single line that you solve the eigenproblem, the associated one, and it turns out that this formula can be evaluated again in a single line, all fully vectorized. You don't have to do any work here whatsoever. And because I could do this, that's the reason why I started working with Julia, because that looks like a MATLAB code, and that's where I come from. I come from MATLAB. So, but I didn't need to do that in Julia, right? I could have done this in MATLAB or in Python. That's the reality, right? No, the hard part is computing the derivatives. And that part I couldn't have done. Okay? So let me show you this next. So for derivatives, you now need to compute derivatives of the eigenvalue problem. Okay? So that here's what that looks like. And that's a little nasty. So this is the first code I wrote for that. And when you look at that, apart from this comprehension, it's still all sort of, you can do sort of nice vectorized notation for that. You can compute it all in this quite simplistic way, and that will work. But the problem you run into is that that's an order n to the 4 scaling. So solving the eigenvalue problem, that should be about n to n cubed, and that's expensive enough, but you have very, very efficient implementations of that, and that saves you, and now you have to do this by hand with n to the 4 scaling, and that absolutely killed it. I implemented this, I tested it, it's correct, but then as soon as I started to try to run my simulations that I described earlier, I would have probably still wait today. So you sit down, look at the algorithm, you reorder loops, and so on and so forth, and you come up with this following idea in the end. It doesn't matter so much where it comes from, that you can write everything in terms of a few order n square loops. So it's a sum over n. So you have a for loop over n. That's the atoms on which you want to compute the forces. You have n atoms. And then inside of that, you have order n cubed, and you cannot change that. That's just life. But what you can do is you can reorder everything in such a way that you have order n square loops plus a single call to matrix-matrix multiplication. So you now have fn matrix-matrix multiplications, and that, again, is so ridiculously optimized that you actually don't feel it. So in this implementation, I never ever saw that matrix-matrix multiplication call. All the bottleneck were in these sort of order n square loops. And this is what I've written here. I still could have written in MATLAB, in Python, wherever, but what I could do in Julia then was that. And that wasn't much, right? That was adding a few extra lines. The code looks a bit uglier, but I have now vectorized loops. I returned with bounds checking, and now suddenly I really get the performance, the best possible performance I can expect for this sort of problem. Yes.
So, given that a lot of people here might not know those macros too, do you maybe want to just tell us really quickly what the macros?
Yeah. So Julia does bounds checking. Whenever you do something like this, it checks that the indices you stick into the arrays are actually within the bounds of the array. If you have an array of dimension 10, you try and evaluate it at index 11, it throws an error. The whole thing crashes. That's an overhead. You add inbounds, everything's a little bit faster. Okay. SIMD, I have to admit, I don't really know what happens in the background, but some guy at Intel, I think, wrote that macro in order to let these loops run in parallel on a processor. But there are restrictions when you can do it. You have to be kind of careful. But anyways, if it doesn't work, it will just tell you it doesn't work, and you don't lose out. So, yeah, but if you want to say more, please go ahead. I'm perfect. Yeah.
I was just going to say what it allows you to do is essentially load multiple values into like a single really wide register, and then compute an instruction on like two values at once or something like this. So it's basically processor level parallelism. And so it's actually I think SIMD requires you to have bounds checking turned off.
That's right. Yes.
So they work really well together as long as you're reasonably sure you're not going to go out of bounds. In which case it will be like, oh, whoops, craziness. Really silly things.
So I should say I'm really very much a user of Julia. I don't get too much in internal. No, that's perfectly fine. And I usually, so these other people who have been talking, you've seen talking, those are the ones I bug when something doesn't work and I need help, and I scream loud enough on a discussion group, and somebody usually comes to help, and that's actually been absolutely wonderful. Yeah. Sorry, did you want to?
I just wanted to ask, chickens and parallel there. Is there some
No.
difference between sync and parallel?
No, apparently something completely different. It puts it on in different. It even creates.
It's totally different.
Yeah, they're very, very different. This is basically simply like the absolute possible smallest like individual instruction level. Whereas that parallel is like starting up whole new processes.
Right.
It's completely together.
Yeah. So I tried to use this new. Because processes are extreme overhead, right?
Yeah.
So with the 0.5, you can technically do parallelization using threads, but as I mentioned to you before, I leave my fingers of that for now. Yeah. So anyways, this was absolute fun, right? And I that way I managed to get my little toy codes to run, but it was no more than that. This was a little toy problem that if I showed that to a material scientist, they'd just laugh at me. But you know, I have my theorem, you know, I have my numerical experiment, I can write a paper, I can publish a paper, and in the past I would have been happy with that. But now I suddenly have far more opportunity. I think that was. So writing code in Julia was fun, but the real opportunity that came with it is what I want to talk about now. And so over the past 2 years, very slowly over time, and then much more over the past few months, I've been developing this package called JuLib, Julia Library for Interatomic Potentials, and a few others, but that's the main one. And really what it does is it mimics in Julia a Python package called ASE, which I thought I'd actually show you quickly. So this is really the model, and so I don't want to claim any originality because the design, everything is really somehow taken from that. Which what it tries to do is it tries to give you a simple scripting interface to a lot of interatomic potentials. So here's a list of different models that you could link to from ASE. And so, but it does a lot more. And I'll show you a little bit about what ASE does. It generates geometries for you. It gives you optimization. It gives you dynamics. It writes files. It loads files in the file formats that are used in this community. And so it's complete madness to try and rewrite all of that from scratch. So what we're doing essentially is wrapping ASE functionality. But now we have, because we do this from Julia, we have the opportunity to write new potentials. So if you write the new potential in Python, you forget it. It's so slow that you can't run anything serious. But now in Julia, we can experiment with new interatomic potentials and write code that's as fast as you'd want for a sort of initial test. Okay, and so let me show you a little bit what you can do with this. So for example. If I want to create a block of silicon, bulk silicon, meaning silicon crystallizes, and so bulk silicon means you get the crystalline structure. So what I can first do is I can write bulk silicon cubic equals true means I get a cubic unit cell of silicon, and now I want this to be bigger, so I multiply the unit cell 3 times in each coordinate direction, and here you go. That's it, and that's the sort of functionality that I don't want to write myself. Yes? And so what happens behind the scenes here is PyCall. For those who've seen it, PyCall calls ASE, it generates the thing and sends me back the information I need. Okay. That's a simple example. I mean, here in Manchester, I think we should try that one. Okay, so you can also do things like this. Or if you want something longer. Okay. So it has a lot of information about materials stored in its databases. So, for example, it knows what atomic numbers are. It knows interatomic distances. It knows the structures into which materials crystallize, and it generates all of those structures for you. I could have written this myself. I could have written this myself, but the next time I want to use something else, and ASE has it, I don't have to write it myself anymore. Right? So that's sort of the point. Okay, so now I want to add a defect because homogeneous materials are boring. Okay, so. I create my bulk silicon, then I extract the positions, then I create a second object where that contains just a single atom at a position that I specify here. Okay, and then I extend my original atoms object with this so-called interstitial. And here we go. Oh, let me just go up and down again. And so what if you can kind of see in here is an extra atom. If we move this around, we can maybe see it better. Here you go. Okay, so there is just an extra atom in there. That's just something that happens during the crystallization process, that atoms are in places where they shouldn't be. So that's a configuration that's not energetically optimal. What happens is these defects have a certain energy attached to them, and from that energy you can there are models that tell you from what the distribution of these defects should be. Okay, how often should you see them? And so I suppose I want to compute the energy of that defect. Okay, so I can do that here. I have to set up my simulation, so I have to add a model, basically. Forget the constraint, that's not important. But I have to add a model, and so in this case I add the simplest model I can find, Stillinger Weber potential, which is what it's called. I can compute the energy, I can do other things. In particular, I can minimize. Okay? And in the end, I can then output this energy difference between deformed, undeformed state, and these are the quantities that you're interested in. Okay? Okay, so what this does is it uses the Julia package called optim.jl, which, if you ever do optimization, you start from Julia, I highly, highly recommend it. It's been a real surprise for me how good the quality of that is. I guess Miles Lubin was again involved in this, right?
Yeah, Miles.
Did a lot of the initial coding?
Sorry.
Did he did a lot of the initial coding?
I don't know the origins story, but I know
Okay.
he has worked on it.
Right. All right. So I can sort of start playing now with real materials, and that's what I want. So okay, now we've equilibrated. This actually, yeah. I think I don't have that much time, so I'm going to skip this part. But quickly, if you wanted to implement your own model, so for example, at some point I wrote down the Jones potential, which is this. Okay, and phi of r is factor minus 12 minus 2r minus 6, except you want to normalize it to take into account the distance. And that's sort of just a very elementary model. And so we have infrastructure to do this in a very simple way. So, for example, that here will generate this intercoming potential. Automatically differentiated, and what this here does is it generates a cutoff function, because if you had just that by itself, you have an infinite interaction range, and so what the cutoff function does is it sort of truncates it somewhere where you think it's safe. And so you can write these things in a very simple way. It looks horrible. I need to work on the output. And then, okay, again, you can create your atoms. You can, so in this case, I'm creating a vacancy by deleting an atom. You can set this calculator, which we just generated here, the model that evaluate energies. You minimize, and okay, you're done. So you can do quite a lot with very little amount of work. But the really interesting part now is to implement new models. So this thing here, which I've done really for fun, should be something much more complex, because an Jones potential doesn't model much. Now I want to put interesting models there instead. Before I continue, can I ask how much time I've got? 10 minutes. Okay. So then there's then I can indulge a little bit here, I think. Okay. So this was a bit of an introduction to this library that I've been developing. Which is a combination of just wrapping this really fantastic ASE library, but also adding functionality that I've been developing in my own research over the past few years, and who knows how that will continue. So I've managed so far to get 2 real material scientists involved in this. Gabor Chani is a friend in Cambridge, James Kermode, a former student of Gabor's, and he's now faculty at Warwick, so it's the 3 of us had a lot of fun with this. And the reason they got involved is because Gabor, like me, absolutely hates Python. And anyhow. So what we're doing is what I described beginning as my research, these how to understand locality, decomposition of quantum chemistry into localized contributions. That's something we're really trying to understand at many different levels. It's an extremely complex problem, much more complex than I showed there, and just really beginning to scratch the surface of it. But they by themselves have started in the meantime using these Julia codes for their own work. And the reason is because automatic differentiation is fast in Julia, and as opposed to in Python, it's horribly slow. So it's not fast enough to do really large-scale stuff, maybe, but it's fast enough to do initial experiments. And they used yet another automatic differentiation package, which unfortunately has broken since the move to 0.5. So now we're gonna try go back to the prototype. Right? That's my next project. Anyways. One thing that we've been working on a lot is geometry optimization, and what I wanted to show you here is if this Python library ASE that I mentioned, the standard geometry optimization you're using there for a very basic problem, exactly the one I implemented for you before. You have a slab of silicon, you put in a defect, and then you minimize the energy, is that red line. Okay, so you got about 900 iterations for a very simple problem. Absolutely awful. And that's actually a standard implementation of LBFGS. Okay. The standard implementation of LBFGS in Optim.jl is this blue line. That's, factored not quite 2, but that looks a lot more promising. But what really absolutely stunned me is the conjugate gradient code. That's the purple line. No, never mind, the blue line. The second blue line. That's absolutely stunning.
Do you know why the different LBFGS implementations are different?
Something different than line search. So Optim.jl has put a lot of work in the line search. I think so. This blue conjugate gradient code here, that's Hagajang conjugate gradients, and I think the line search. I quite like optimization. I spend time with it, and I'm not even close to understanding how many things it does. Very robust, very careful in how it does things. Right. So when we started working on that, we actually weren't using Python, we weren't using Julia, we were using a Fortran code that Shani and Kermit had been working on for a long time. And I think it took us 2 years to get everything to run that we wanted. So fix the optimization code, put in our preconditioners, get everything to work efficiently, right? Because you have to interface. I need you need efficient linear solvers for it when you have preconditioners and so on and so forth. And we then did it in parallel in Python and Julia. And well, okay, I think in Julia it's something like 20 lines on top of what already exists, and in Python it was maybe 100, but it was fabulous. Anyways, that's these green and red lines here. So those here are modifications that we made to the BFGS codes and the preconditioning capabilities we built onto it. That so far that doesn't exist in plain Optim.jl, only in a branch that I have. I'm waiting for some things to merge, but with very little effort you can make huge gains here, just because you have such easy access to the libraries that you're using. So that was one thing I wanted to bring across here. So I mean, it's optimized for our specific applications, specifically for molecular simulation, but who knows, maybe some parts of it will be useful for other people as well. All right. One of the things we've been working on is saddle search. I just put this in because I had some fun playing with plots.jl, and so what happens in saddle search, this is a toy model, it's not a real problem. You put 7 atoms in the plane, so they're not allowed to move out of the plane. But you can see if I take 2 atoms and swap positions, then it's the same configuration again. And so you have 2 minima in the energy landscape, and now you want to find a path between them that's somehow optimal. Right? So you don't want to go over maxima, you want to go through the saddles on this path. That's the idea, and not describing the details, but you can beautifully just visualize this process. And I think that's something I did. It took me 20 minutes to learn how to use plots.jl and another 20 minutes to write this. The ease of use of the Julia libraries is fantastic. Okay, but back to sort of real real problems. Okay, so I said I wanted to now go from my toy problem in the beginning to real molecular simulation. So one thing we did is we implemented a tight binding model. So if you don't know what tight binding is, don't worry about it. It's sort of a semi-empirical electronic structure model. It's still not the real thing, but it's closer. And so, for example, what I do here is I create. So it's not silicon this time, but carbon. I don't remember why I made that choice. But I create a unit cell, a 4 by 4 cubic unit cell of carbon. And now I create a tight binding model with that. I can now compute the Hamiltonian matrix. And what I wanted to show you, just quickly to motivate this, is if I have 500 atoms, which is a low number, I'm more interested in thousands of atoms, then I have actually multiple electrons attached to each atom. In this case, it's 4, but it could be 9, and so the Hamiltonian size becomes much bigger. And so the cost of doing these calculations is somewhat higher. I think what happened here is, give me a second, that I've overwritten something accidentally that I didn't want to do. Yeah. Okay. And so just evaluating the potential energy for one configuration now takes 10 seconds. Okay. So it's large configuration, 512 atoms, 10 seconds is okay, but if you need to do this over and over and over again, and what I explained in the beginning, the site energies, this localized, this decomposition is much more expensive than plain energies, so everything gets exacerbated. And so some of our old codes, they didn't scale. We needed to write new codes, and I wanted to show that here because that's actually a technique that I think people in Manchester are working on, in the linear algebra group, that use contour integration to evaluate these site energies. And again, you have incredibly simple ways to implement that in Julia. Again, that could have been in MATLAB or Python, whatever, but then going further and actually implementing the site energies and so on and so forth, and the derivatives, that was harder. And so at least I wanted to show you quickly what I can do now with this. This is now, so it's not the model I'd really like to use, but it is a good step towards that, and I can now test what these constants in my estimates look like on something that people would consider a real model. So if I take that model to a material scientist and show the results, they wouldn't laugh anymore. They'd say, okay, that's interesting. Let's now look at that on model such and such. But you can see, I mean, this thing's running in the background. It's already taking time to compute these site energies. Yeah. So 27 seconds, that's sort of what I expected. And what I can do now is I can test how good this locality really is in my models. I obviously have a problem with yeah. So the red line here would be the tolerance, and that tells me sort of everything that's below that are forces that are so small I don't care about. Everything above that, those are the forces I keep, and now I can count how many that is. That's 57 atoms I need to keep, and that is low enough that I am happy with that decomposition. So this is a quantitative result now on a real model that I can take away to use to continue with my simulations on something resembling a real model. Okay. So, but I told you that's not quite the right model, so I need to go a level further, and so I thought, okay, and I did that this morning just because I could, basically, right? So I got another Python library that is called GPaw, that is a full-blown electronic structure code that will do that's what material science actually use day-to-day practice, and I added that as a calculator to my silicon cell again. But now what you notice is I don't multiply that anymore. I just keep a single unit cell here that contains 8 atoms. And if I now evaluate energy, wait a minute for just 8 atoms. And I'm doing this, so if you know anything about electronic structure, there's the number of K points I'm using is essentially illegal. You're not allowed to do that. It should be much more costly than that. So the cost of these codes just explodes. And this is why I use this hierarchy of tiny toy models and then sort of slowly go up to more and more sophisticated models to try out what really happens. So yeah, it's 22 seconds to just evaluate the energy of a single unit cell. Right, so let me quickly wrap up. The main message I want to bring across is you can really use not just Julia in general and specifically these libraries that I tried to show off a bit, to go from very simple toy models to sort of prototypes you use for your research to actual codes that one could then use for maybe real material science. So that last step is something that we haven't done yet, but that's one of the next steps. And that's why I got excited about it, really. Because it's so easy to interface existing code, existing software, and yeah, I can stress test my new algorithms on not just on my toy problems, but on real problems. All of that's been incredibly valuable for me. And okay, we're going to do a lot more. I'm not going to go through this list. You can stare at it. But so maybe the one thing I wanted to emphasize is what I really try to achieve with this library. I want to make it accessible to mathematicians, primarily myself, but my research group, hopefully more, while at the same time making it useful for an actual material scientist. And just bridging that gap, that was the aim of this, and we'll see how that develops over the next year or two and whether that succeeded or not. But there's a huge need for better algorithms in molecular simulation at every level. It can be things as simple as optimization, but the real need now is, I think, primarily in sampling, so in free energy calculations. And sort of electronic structure is moving to new levels these days, so there is a lot more to do there as well. And I really hope to get, especially molecular analysts, interested in this, because there's just so many things to do, and so many things that I cannot do myself, really. So maybe one or two might get interested of you. But yeah, thank you for your attention. And
any questions? No. Oh, yeah.
So elast is infinite, right?
the what is infinite?
Elast is
Yes.
like in the real world, but infinite.
Yes.
How do you impose that on the outer boundary? When you talk about forces,
Yeah, okay.
levels, so is that issue of crack propagation basically?
Good question. This here?
You know the crack propagation animation?
Yeah, let me start with that one, then I'll go to Cracker. So I'll make something explicit that I didn't write out. PBC, periodic boundary condition. Okay? So you can do that. You cannot do that for a crack. So another thing you can do, and that's a little, you can't just implement that with a little line, clamp boundary conditions. I put something on the outside that somehow mimics what the outside crystal is. But if I now go back to what I was trying to describe to you as my research, that's actually exactly what this is about. So there's this far field, the black part, which I don't model, and I somehow need to understand what the error is that I've made by not modeling that. Okay? And that is true for this toy model on the screen, but it's much more true for the crack propagation problem that you've seen later. And so that is actually exactly what these error estimates quantify. So you cannot model an infinite crystal. You have to model a finite subset, and then you have to just understand what the error is. Okay. And in this case, and so what you actually do is you define the infinite problem as a limit of finite cell size problems. And that's true for all of these. The crack problem, the interstitial problem that I showed you. Yeah. And the harder, so for a little point defect, that the rate is diameter to minus dimension over 2, that's a good rate. But it's not fabulous. You get rates like this black line here. But it gets much worse for harder problems like dislocations, like cracks. And this is exactly why these sort of multi-scale ideas come into play. Is that actually answering your question? So in the crack, let me just go concretely to the crack so you know what one does here. Come on. Oh, it was at the top, right, wasn't it? This one, right? So what happens here, this is actually much bigger. And what you do is you clamp atoms at the top and bottom edges, and you just pull the crystal slightly apart to open the crack, and that creates a stress field that acts on the crack tip, and that drives everything forward. That's concretely what you do in this case. Yeah. But there's an error associated here with the size of the domain, with the size of your computational domain, which you don't see here. And that's the numerical analysis part, the part that I'm really interested in at the bottom of all of that. Yeah. So I've never tried annealing. I'm sure you could do it in principle. But so what you could do is, let me actually go back here for a minute. Here. So what that does, these 3 lines here, or 4 lines, they generate a bulk silicon crystal. They then add to that crystal a GPAW model. That's LDA. It's sort of find a difference code rather than a Gaussian code. Okay, it's meta. You could attach something else, and then what you can do with this is you can evaluate energies, forces, anything you want. So if you prefer Gaussian to GPAW, well, just go to ASE, look up what it is that you really want. GPAW is the one that I used. Here's Gaussian. Okay, there's a Gaussian that you can attach Gaussian to ASE. So if you have that implemented on your computer, if you have that installed on your computer, which I don't, then you could do something like this. You change 1 or 2 lines here, and then you can run with Gaussian. Right? So of course this won't help you because you already have a crystal. Now you'd not want to generate random species, but that should be an easy enough script to write here. Yeah, I'm sure you get gradients from Gaussian. I'd be very surprised if not. But do you need gradients in simulated annealing? I don't know anything about simulated annealing. Yeah. So, yeah. So if people look for crystal structures, typically what they do, they generate random configurations and then do classical minimization. Right. 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 Okay. Well, okay. Tell.
It's not my area.
Yeah.
It's
Got it. Okay. There's something called. Let me see if I remember it. Yeah, it will come to me after I stop talking, but I'll give you a name to look at. Right. Thank you. Okay, thank you.